Hi, this is Dane Quinn, and I'm from the University of Akron. Today I'd like to talk about how we solve ordinary differential equations numerically using MATLAB. So first, a little bit about why we might want to do this. Well, really engineering systems are often modeled by ordinary differential equations. So for example, the spring mass damper system that we see over here on the right, its response is determined from the solution to an ODE, right? And it's a very familiar form, mx double dot plus bx dot plus kx equals some forcing, right? So here the mass is m, b is the damping coefficient, k is the stiffness, and x measures the stretch in the spring. In addition, we have some initial conditions, right? So we might displace this block over by some value. We might give it an initial velocity, and then in order to determine how this system behaves, we need to solve this equation. So, for example, if we assume that the forcing is constant, let's just give it a value w, and let's let the initial velocity be equal to 0, then we can find the exact solution, right? We can use the method of undetermined coefficients, with particular solution, homogeneous solutions, and we end up with this, right? So this is basically a constant offset due to the force, and then this describes the transient solution. Right, so again, we have a particular solution, we have a homogeneous solution, and more importantly, or as important, we can identify the dependence between the parameters of the system, right? These physical parameters, m and b and k and maybe w, and the characteristics of the response, right? So for example, this response decays exponentially, right? And the envelope is sort of denoted here in these dashed green lines. And well, that decay rate is b divided by 2m. Right? We can also identify the frequency of the oscillations, right, given here in terms of m and b and k. The offset that this solution tends to, right, we can define that. That's the weight, or w divided by k. Right, so really, we can use these exact solutions to understand how the forcing, the system parameters, and the initial conditions, right, x naught here, influence the response. And the reason that we want to do this is because as engineers, we want to design things, right? So we want to be able to pick the system parameters so that we get good performance, right? So that's great. Exact solutions allow for that. However, and there's always something, exact solutions are not always available. So they don't always exist. At least in terms of sort of simple elementary functions like sine and cosine. Right? So at this point, we have to turn to numerical solutions. Right? Because again, we can't solve an equation. This one we can, of course, right? But there are some equations that we can't solve exactly. Right? So we have to have numerical solutions. So these numerical methods can be used to approximate the solution to these differential equations, and they're fairly flexible, right? We can have arbitrary forcing, right? We can have nonlinearities, right? So for example, we could solve for the response of a pendulum. We can easily have multiple degrees of freedom, right? But there are some problems with these. The solution is only generated for specific initial conditions and, perhaps more importantly, specific parameter values, right? So, for example, remember these were like m and b and k in the system, spring mass damper system that we had before. And in addition, right, the solution is only generated, right, and it's an approximate solution at discrete points in time. Right, so we'll kind of list these as t sub I. So for example, we might have an initial condition, right, x0, And then our numerical solution might approximate the exact solution, which is sort of shown here in blue, right, with this response, this value of x at the next time, right? And then it might take a step of time in the future, right, and find x2. And then at t3, we have x3 and so forth, right? So again, this part is good, right? Because there are a lot of problems that we don't have exact solutions for. But unfortunately, this is, well, it can be limiting, right? So again, if you want to do engineering design, you might want to know what happens to the system as we vary these parameters, right? So from a numerical standpoint, we might have to run lots and lots of simulations to understand how the response varies with these parameters. But again, if exact solutions aren't available, kind of don't have a choice. So let's look at perhaps the simplest and starting point for numerical methods, which is known as Euler's method, right? So let's consider an ODE of the form x dot is equal to g of x and t, right? So this is fairly general, right? So here we have the derivative as some function of the state x and time. So now if we think about a Taylor series, right? You have come across these before. Then any function, right, say x of t, which would be the solution to this differential equation, can be expressed as x at some time, say t star, and then we have the derivative of x with respect to time evaluated at t equals t star times t minus t star, right? So again, t star is some arbitrary time, right? And I can write out a Taylor series for this function. And of course, there are higher order terms, so quadratic and cubic and whatnot. But if you really look at what we have here, this ordinary differential equation actually defines this term, which really represents the slope of the curve. So we can turn this into a numerical method, right? So let's let t of I plus 1, right? So we have the next time is equal to the current time plus some delta t, right? So think about, I is equal to 0, we'd be looking for the response at t1. Or if I is equal to 3, sometime t3, we'd be looking for the response at t4. So if this becomes my t star, then my Taylor series approximation becomes x of t I plus 1, right? That's the new time, is equal to x of the old time, which will start at ti, plus now the slope or the derivative, but that comes from the differential equation. Right? So basically g of x, and again, this is evaluated at ti, right? So it's the position at this time that we're starting with, and the time times delta t, right? So delta t is the time difference between these two things. So for shorthand, we'll often define this x of ti as x of I plus 1, right? This would be x of I. And as a result, we see that x at the next time, right, ti plus 1, is equal to x at sort of the current time plus g of x ti and ti times delta t, right? So really, what we have is an algorithm to march forward in time, right? So given a current time and a current position, x of I, we can go and use this. This is again Euler's method to find t of I plus 1, right? Because that's just ti plus delta t. and then the new solution. Right, so now we have a way of sort of marching forward in time. Given this x0, right, we can use this to calculate x1. And then given this x1, right, we can use this to calculate x2. x2 gives us x3 and so forth. Right, so part of the problem though is that, and you can kind of clearly see this here, each one of these is an approximation. So the error begins to build over time. Well, there are more advanced methods that try to help with this accuracy. They have different error properties, they're more accurate, and so forth. But Euler's method really is a starting point for understanding how numerical methods work. This lecture is not about how we come up with advanced numerical methods. This lecture is really about using numerical methods that have been developed elsewhere, right? So MATLAB has a number of built-in functions for numerical simulation, and one of the ones that is most common is ODE 4.5, right? So that's the one I'll focus on here. Other numerical methods have a very similar structure and very similar use. So this is essentially the description of ODE 4.5 that I took from the MATLAB help function. And it describes the inputs, the things that MATLAB needs to numerically simulate, and then the results. Right? So essentially, ODE 4.5 integrates a system of n differential equations. So the previous example, we just had one equation. For example, we had one coordinate, but we can actually integrate a whole system of first-order equations using MATLAB, right? So in particular, we can integrate n of these for n state variables, right? So S is going to represent all of the different coordinates that are in the system that we might need. And then the equation that describes how S changes, right, the differential equation, is given as S dot equals some function g, right? So very arbitrary at this point. And of course, MATLAB needs to know what this differential equation is, and that is defined in the function deriv.m, right? So that's the file that we would write to describe the equation that we want to solve. And that file name goes in the first argument. We also need to know initial conditions. So here, S0 would be the initial value of the state variables. And of course, we need to tell MATLAB how long we want to simulate for, right? So tspan tells us the interval over which we simulate, from t0, right? It doesn't have to be 0, but typically is, right, to some tf, t final, or some t max. MATLAB also has a place that you can put in optional integration variables, right? So for example, if you want to control error tolerances, there are lots of things that you can do with these, right? And that would be set through these structure options. Right, so again, these state variables might have n different coordinates, right? So x1, x2, all the way up to, however many coordinates and equations we have. And then that is what is output, right? So the result of this is S as a function of t, right? So it would be x1 as a function of time, right? x2, the second coordinate, as a function of time, right? And as mentioned before, the time is given at discrete values. So we'd have a whole series of times at which we produce this solution from t0 to t final, right? So if I think about how MATLAB actually uses this, right? Essentially, we have this ODE 4.5, right? That's our MATLAB function, and it needs the initial conditions, right? And then it gives us S and T, right? Of course, T is T0, T1, all the way up to T final. And S would actually be a big array of coordinates, right? So each one of these S's is going to have all of these coordinates in here. So it would give us S0, S1, S2, right? So those are all the solutions at these various times that MATLAB also gives us. So again, our solution is generated between t0 and t final, but we have to tell MATLAB what the function is that we want to solve, right? That makes sense, right? So essentially, this deriv.m file defines the ODE, right? And this is something that we have to write. And then all of the stuff in here is sort of within MATLAB, right? So essentially, this deriv function takes in the time and the state variables, right? So all of these coordinates at some value, and gives back to ODE 4.5 the derivative, right? So basically, ds dt, again, at this time, right? So within this, we are essentially defining the equation that we want to solve. So again, kind of here over on the right, so this differential equation is defined within the deriv file, and it's a user-defined function, right? Typically put into a file. Again, I'll call it deriv.m. You can pick any file name you want to, right? But the structure is you have function, right? This tells MATLAB it's a function. S dot, and that's going to be the output. Deriv, that's the file name, and then these are the inputs, right? So these two things are the inputs, and S dot is the output. And we'll obviously show you an example of this, right? But essentially within this function, we are defining the derivatives as a function of time and the state variable. So let's actually do an example. We'll start off with a first order example, or a first order equation. This is probably the simplest thing I could come up with, right? So basically x dot plus sigma, some decay rate, times x is equal to 0. And we have a single initial condition, and we just have one coordinate here. So really, this quantity, these state variables s that we talked about earlier, is just x. Now, MATLAB needs to know the derivative of x, right? But we can solve for that from the differential equation, right? So essentially, x dot is equal to minus sigma, right? This becomes what goes into our derivative function. Now, I will note that the exact solution here is easily obtainable, right? So the exact solution is x of t is x0, the initial condition, e to the minus sigma t, right? So let's actually solve this numerically and compare with the exact solution. And I'll pick sigma equals 2, and the initial displacement is 5, right? So again, I've got to define a derivative file, right? So here, function, this is the derivative of x. This is what I'm going to call the file, deriv first order .m. I'll go ahead and define this parameter sigma inside this function. And so then here, x dot is equal to minus sigma times x. Right? So again, this function takes in t, which actually is not needed here, right? But there are cases where it is. This takes in t and x, right? So the current state, and gives MATLAB the derivative of that state, right? So again, here x dot is minus sigma x. So here I have the MATLAB code that will actually simulate this equation. I've written it out, right? So if you want to pause and you can go put it into MATLAB, that's fine, right? But I thought I'd actually show you using MATLAB. Right, so here I have my MATLAB command window. So the first thing we need to do is obviously define that derivative function. Right, so let's go through and open up a file here. And we'll type in what we saw on the previous screen. Right, so function, this tells MATLAB that we're defining a function. X dot is equal to deriv first order as a function of t and x. So here notice that I used x rather than s. You can use any variable that you want to for these things. MATLAB doesn't care. For the parameters, we'll take sigma, and we have to define this, is 2. X dot is minus sigma times x. Notice that I put semicolons after these statements so that MATLAB doesn't give an output every time it goes and checks these things. And then we'll just end this function. Okay, so let's go over and save this. MATLAB will typically choose a file name for you. You can obviously change it, right? But if you have a function, it will try to intelligently choose the name of the function. So now we have defined our function, deriv first order. Let's go and actually simulate this in MATLAB. Right, so remember that for our ODE 4.5, we need the deriv function. Well, we just did that. We also need the time interval, t is initial to t final, and we need the initial conditions. Right, so I'm going to go and set t max. So that is going to be my final time. Right, so here I'm going to integrate from 0 to t max. Let's let that be 10. My initial condition, x0, is going to be 5. And then here, ODE 4.5, t comma x, these are my output variables, the time and at which we determine the solution, and then the solution itself. ODE 4.5. Next is the function name that I'm defining the derivative. Notice that I put this at sign before the function name that it tells MATLAB that it's a function handle, and it just works better. And then my integration time is 0 to t max. Right. I do this so that if I want to go back and simulate a longer time or a shorter time later, all I have to do is just change t max. And then I can use this command again. Same with x0. Right, so there it is. That's MATLAB's ODE 4.5 for this function. Right, let's hit enter. Oh, there it goes. It doesn't take long at all. Okay, so now we want to look at the exact solution. Remember that was available for us. So here sigma is equal to 2, and let's go and define the exact solution. So that was x0 times e to the minus sigma times t. So again, fortunately in this situation we have an exact solution, right? So I can compare. There it is, it just calculated it. And notice that it calculated it at the times that were determined from the numerical simulation. You could actually go and define a new time variable and ask it to calculate the exact solution at other times. But I'll just use the times that came from the numerical simulation. All right, so let's go and plot this. Here I'm going to plot t comma x exact. Right, so I'm going to plot the exact solution in red, and then I'll plot the numerical solution, right, which is was given as x, as a blue solid line. Right, so the red solution will be in dashed. That's the 2 hyphens here, and then the exact the exact solution. So the exact solution will be given in red, dashed line, and the numerical solution will be a solid blue line. All right, so let's hit enter. There we go. Notice that you actually don't see a red dashed line, right? Because ODE 4.5 is really very accurate, right? So here, essentially the red line sits underneath the numerical solution. If I go and I zoom in, I might be able to find these two things. Kind of start to see a little bit of difference here. Right? So again, there is some difference, right? Because the numerical solution is just an approximation, right? But that difference is really very small. And using those optional integration variables, right, that are passed into ODE 4.5 from the options structure, right, we can actually control how much error exists in our solution. But again, in this case, it's really very accurate, right? So we see that, as expected, right, our numerical solution just decays exponentially in time. It ends up getting really small by 10 time units. Okay, let's do a more complicated example. Typically, we deal with higher order equations, right? So second order equations, third order equations, multiple degrees of freedom. Well, MATLAB really only takes in systems of first order equations. But fortunately, we can write higher order equations as a system of first order equations by identifying higher derivatives, right? So let's look at that spring mass damper system that we had at the very beginning. Here, let's assume we have zero forcing. The equation of motion was mx double dot, right, plus bx dot plus kx equals 0. And then, of course, we have some initial conditions given as well. So how do we identify these higher derivatives? Well, basically, we identify every derivative of x as a new variable all the way up until the second highest, right? So here, we'll identify x dot as the velocity, right? So if you look at this, the derivative of x dot is v, right? So this is a first order equation. And then we want to identify the derivative of v dot. Well, v dot, again, is x double dot, right? Because again, x dot is equal to v. And this now comes from the equation of motion, right? So let's solve this equation of motion for x double dot, right? Essentially, we get minus 1 over m times b times x dot, but x dot was equal to v, plus k times x. Right, so again, this comes from the equation of motion. And by identifying these higher derivatives, we can write this as a system of equations, right? Because x dot is equal to v, v dot is equal to this term on the right. I can always express this in matrix form, right? So here, s of t, right, these are my state variables. It's going to be x of t and v of t. Right, so MATLAB is going to solve for these two things separately. And then the equation of motion in first order form is x dot v dot. Right, so here I can actually write this as a matrix. X dot is equal to v. Right, so really I'm going to write this as a matrix times the state itself, right? Because remember, the state is x and v, right? So here, x dot is equal to, well, it's 0 times x plus 1 times v, right? So x dot is equal to v. V dot is minus b over m times v, and then minus k over m times x. Right, so really, this looks like a matrix times the vector of states, S. Now, if we were to go and use Euler's method, on this second order equation, or really two first order equations, we would have S I plus 1 is equal to S of I, right? So here, S of I is equal to S at ti, right? So S of I plus 1 is S at this new time, plus Si dot times delta t, right? Euler's method looks exactly the same, just now these are quantities or vectors rather than just a scalar quantity. Using our equation of motion, right, we have S of I plus now A S I times delta t. And of course, our initial condition is S of 0, right, which is going to be x of 0 and v of 0, or x naught and x naught dot, right, because this is v of 0. Right? So again, we can define our initial conditions, and we can go and use MATLAB to numerically simulate this. Right? So again, I'll show you the derivative file. Right here, I'll define it as deriv smd, spring mass damper, .m. And this function that we're going to define returns s dot, right, which is basically this quantity here. So again, let's actually go to MATLAB and show you this. Okay, so I want to clear everything, start fresh. Let's define a new function, right? That's going to be the derivative file. Function s dot equals deriv smd, spring mass damper, t comma s. Right, so again, we have inputs. We're returning the derivatives of those. Just like before, I need to go through and define those derivatives. Now, just as a hint, MATLAB needs a column vector. By default, if you just say like S1 and S2, it puts it in a row vector. So I tend to always start off and initialize S dot to be the right size. And I just write it as the size of S. Right? So this is going to take in a column vector, and I need it to return a column vector. Right? So here I'm just initializing S dot to be a column vector. Some parameters. Let's let M to be equal to 2. B, let's choose that to be 1. K, the stiffness, 32. Why did I choose these? I just did. Now, I usually try to make my MATLAB code as readable as possible. S1, S2, right, elements of a vector, that's not terribly readable for me. Right, so I'm going to go and say explicitly that X is equal to S1. Right, so here again, S is a vector. The first element of the vector is going to be X. Second element is V. Right, I'm just going to rename these so that I am able to keep it straight. V here is S2. You don't have to do this, but it definitely makes your code more readable. So here, X dot is equal to S2, and V dot is equal to the equation of motion. Right, so that's minus B times V plus K times X divided by M. Right, so this is now our equation of motion. Remember, X dot is the velocity. Velocity is V2, or S2, which is V. V dot is the acceleration, which we get from the equation of motion. And then we need to output these two things. So S dot is equal to X dot, and then V dot. So there it is. There's our equation of motion defined in MATLAB. Let's go and save this, see what happens. Oh, look, it pulls up the name of the function. So that's good. So we cleared our workspace. So everything is started. We're starting fresh. So let's go through and use MATLAB to numerically simulate this again. Once again, I'll start off with Tmax. Right. So let's integrate for 20 time units, 20 seconds. The initial displacement we'll take to be 5. Let's choose the initial velocity to be 1. Right? Again, these are kind of arbitrary. And so MATLAB needs those initial conditions as a vector. Right? So really x0 and v0. Right? So IC represents our vector of initial conditions. This is like S of 0. And at this point, right, we're ready to simulate. T and S, right? So now we're going to output the states as S. ODE 45. Again, at deriv SMD, spring mass damper. Integration interval, 0 to T max. Initial conditions. Right, so here we have it. Hit enter. There, we've got the solution. Again, for readability, just so we are aware, if I look at the size of S, so that's our solution, it has 421 rows and 2 columns. So for readability, right, I'm going to go and say that S is equal to all of the rows and the first column, or X is equal to all the rows in the first column of S. Again, careful to put semicolons so it doesn't just flood my screen with output. V is equal to S, all the rows, the second column. And now I can plot the position and velocity. All right, so let's plot the position in red and then the velocity in blue. So there it is, right? It came up in the same figure, right? Notice that the initial position is 5. The initial velocity, right, if we were to go in and zoom in near time 0, right, the velocity starts at 1. Zoom back out, right, and we see that we have this characteristic decayed response, right, due to the presence of damping. Right, so we have some exponential decay of the system, right, both in terms of the position and the velocity. If we want to be, want to kind of keep track of what's what, let's label the x-axis with t, right, so that puts a little label down there. Let's put a legend in there. X is going to be the first thing that we print or we plotted. So that's the position. And then the second thing we plot will be the second legend entry, dx dt. There we go. So again, using MATLAB, we have been able to numerically simulate a couple of different codes. Or different systems. We did a first order system, we did a second order system here. So that's a good introduction, I think, to the use of MATLAB for numerically solving differential equations. Thank you very much. I'll do some more examples. I'll do some more complicated and involved simulations later. Right? I'll show you how to pass parameters and variables into the derivative function, talk a little bit about options, but this is a basic overview. So thank you very much.